In this problem, we're given the proton NMR spectrum and the molecular formula C4H8O. So the first thing I'm going to do is calculate the degree of unsaturation. And we'll do that by taking 2 times the number of carbon plus 2 minus the number of hydrogen, which is 8. And then we don't have any halogens or nitrogen to deal with. We ignore the oxygen. Divide that by 2. So this gives us 2 divided by 2, which is 1. So the reason that's useful is because that tells us in our final structure, we better have either a ring or a double bond. So the next thing I'm going to do is go through this and give an assignment to each of these peaks. And just start by giving it a CH assignment, either making it CH, CH2, or CH3 based on the number of hydrogen it's integrated for. So first, we have a 1H integration, so I'm going to make that a CH. And I have a 2 hydrogen integration, so I'll make that a CH2. We'll do another CH2, and finally a CH3. Right, the next thing you want to do is go through and check and make sure you have the appropriate numbers of things. For example, you need to have 4 carbon written out, and we have 1, 2, 3, 4, so we're good there. We need to have 8 hydrogen written out. We have 1, 2, 3, 4, 5, 6, 7, 8, we're good there. The only thing that's missing is an oxygen. And I want to get that down as sort of a puzzle piece, so I'm going to write my oxygen right here. The next thing I want to do is go through, and I just like to put little dots on each atom to indicate the number of additional bonds it needs. So remember, carbon always wants a total of 4 bonds. So if we've just written CH, that means this carbon needs 3 more bonds to be complete. A CH2, the carbon needs 2 more bonds. Again, 2 more bonds, and a CH3, 1 more bond. Now there's one thing I can go ahead and do here just based on chemical shift. So a lot of times you don't need to look at chemical shift right away, but it's pretty helpful in this case because we have something down here in the 9 to 10 region. And there's really only one thing that tends to show up down here, and that will be the aldehyde functional group. So what I can do is go ahead and simplify a couple of things and make my aldehyde fragment. And the aldehyde will be a CH double bonded to an oxygen. So here's what the aldehyde looks like. Now that I've drawn that though, be really careful that you don't leave fragments around and end up using them twice. So what I want to do is actually cross this out and cross this oxygen out because I've combined the carbon and that oxygen to make this aldehyde. And now, because we've used 2 of those electrons to make the double bond to the oxygen, I just need 1 more bond to this carbon. So we have kind of the pieces to our puzzle here that we need to put together. And what we can start to do now is use our splittings to figure out maybe how to connect some things. So you might come down here to this triplet for the CH3. A triplet will be n plus 1 equals 3, n equals 2. So that means this CH3 is connected to a CH2 group. But we have 2 to choose from, so how do we know? Well, we don't right away. So what you might do instead is then move on to another signal and think about it. Well, let's go to this CH2 group right here. This is a sextet. So that means N plus 1 equals 6. N equals 5. That means this CH2 group should be connected to carbons bearing a total of 5 hydrogen. Well, what would that be? We can connect it to the CH3 group, that accounts for 3. We can connect it to this CH2 group, that accounts for 2 more. So now we're pretty much done here, because if you start to look, you don't have to do much more analysis, because we have 1 dot here that needs a bond, 1 dot here that needs a bond. Connect those together, and we've bonded everything up, and we're done. So now what I like to do is just draw out the molecule, making it look a little bit nicer. Here's our aldehyde, bonded to the CH2, bonded to another CH2, bonded to the CH3. In terms of just kind of reviewing the chemical shifts, we already found the piece that was in the aldehyde region. The only other kind of important region here is this one at about 2.3. That's in what we title the allylic region, meaning it's bonded to a carbon with a pi bond, and this carbon is bonded to the carbonyl. One other thing, which is just good to mention here, that way there's no confusion. You very well might expect this aldehyde to show up as a triplet, because it's on this carbon. The adjacent carbon has 2 hydrogen. You might expect that to be a triplet, and the CH2 to be split with the aldehyde as well. That can happen, and it's something that might be expected. It just tends to be the case a lot of times that the aldehyde sort of breaks your coupling, or the coupling is so small you can't see it. So in many cases, even if there's a neighboring CH group, aldehydes will often just show up as singlets. So my best advice there is just don't box yourself into a corner. If you see splitting in the aldehyde peak, don't be surprised. If you don't, also don't be surprised. So that's one that can cause a little bit of confusion.